to CS577a. Today is Monday, October 14th, 2019.
Is this mic on? Yeah. So let me make a couple of announcements before we begin. PC1 regrading is going to be tomorrow. So make sure that you take advantage of that if you have questions. And IC1 to IC5 should already be graded. If you don't see your score and you know that you submit or you have any questions, don't forget you can post it on Piazza or email me or Professor Su on that. And you have to submit this WinBook and prioritization report. But due to the reason that WinBook is down right now, I might change the deadline for that. Just keep an eye out for it. Yeah. Any question on anything? And next week is your ARB presentation. Hope you guys ready for that. It's your mid-semester grade, so it counts a lot for your grade. Okay? Any question on anything? Okay, so today we have a special guest speaker. So let's look at his bio. So his name is Doug Rosenberg. So he's our alumni, USC alumni. He graduated at USC in 1980 in electrical engineering. So he has authored multiple books. So the most popular is Use Case-Driven Object Modeling with UMLs right here. It's also available on Amazon. So he has trained hundreds of companies in UML over the past 26 years. He has been developing parallel Agile process and testing it on student projects at USC for the past few years. Also, currently mentoring teams of directed research students for CS590s. He is now a founder and CTO of Parallel Agile Incorporation, or this, you can go to this link. And his new book on Parallel Agile is coming out soon. Here is the picture of the book. So if you're interested in that, just talk to him after. So give a warm welcome to Doug Rosenberg.
Thanks, Ken. So I guess let's do a mic check. You guys hearing me all right? Okay, so I actually have two sets of slides that are a little bit redundant. The first one is going to give you an overview of what Parallel Agile is, and the second one is going to go into some specifics on what we mean. The book's subtitle is Faster Delivery, Fewer Defects, Lower Cost. And we're going to get specific about where those improvements come from in the second set of slides. So, also, let me just say, the book is in final production. We're supposed to be reviewing page proofs actually next week, and it's supposed to come out in November. I have copies of the book in PDF, the complete manuscript. If anyone wants one, you can email me or connect to me on LinkedIn and just send me an email saying, hey, I'd like to get a copy of the pre-release manuscript, and I'll be happy to send you one. So, okay, so Parallel Agile is our attempt to enable large team development for software engineering. It's kind of like there's an old saying in basketball, a good big man beats a good little man, right? So sometimes you'd really like to be able to take a big software project and throw a large team of people at it and get it done quicker. And the conventional wisdom in the industry has been that this is impossible. But we've been doing it here at USC, and we've been having really good luck with it. It starts back, it actually started in this classroom in 2014. Professors Beam and Kulmanajwang have been in the habit of inviting me to give guest lectures just like today for several years now. And back in 2014, I had an idea for a project that I wanted to get designed. It was a location-based advertising system, basically mobile coupons using geofencing so that when you walk up to a store, you get a coupon on your phone right before you get to the front door of the store. And so when they invited me back in 2014, I said, sure, why not? And if you want, I can grade a couple of UML homework assignments for you. And they said, okay, sure, that's cool. There were 47 students in the class that semester. So I took my mobile coupon system and I split it into 47 use cases, and we handed out one use case to each student in the class. And the homework assignments, there were two homework assignments. First one was called Build the Right System, which is basically requirements modeling. Second one was called Build the System Right, which is basically design. And as I was grading the first homework assignment, I realized that this thing was going to go pretty well. And I suggested, if you like, you can assign an optional extra credit where students can deliver a prototype of their use case. And 29 students decided to do that extra credit assignment. And I said, and we better keep track of how many hours they're spending. So we did. We tracked hours on the project. And what it sorted out was it was across probably about 4 weeks. I think the two homework assignments each had a 2-week, time span. And it wound up being 8 hours per use case, or 7.7 hours on figuring out the requirements, 7.6 hours in doing the design, and then 12.7 hours to write prototype code and test it. And it totaled out to 26 hours per student. And I looked at that number. We'll come back to that number in the second set of slides, but I looked at that number and said, yeah, this is pretty good, because multiply 26 hours per student times 30 students, and we just got a whole bunch of hours worth of work done for not very much calendar time spent, okay? And so that told me that, large-scale parallel development actually is possible. And we spent the last 4 years now repeating this process, okay? And at the highest level, the process is you basically spend some time when you're starting the project to set it up so you can do parallel development. And then you do everything else in parallel. One use case at a time. You basically figure out your requirements, figure out the design, and build it. And so since you're in Professor Bame's class, I'm sure you all know what the spiral model is. And what we do in Parallel Agile is we basically apply the spiral model, but not across the whole project as a large entity, but we apply it one use case at a time. So we split our system into use cases, and then we go through this ICSM spiral. And it starts out as build the right system, build the system right, test what you built, and it ends, in another way to phrase it is you go through a proof of concept phase. Whoops. You go through a proof of concept phase, you go through minimum viable product, and then you optimize it. And then the techniques we use is we do a lot of prototyping in the proof of concept phase. And we combine this. We kind of have a little secret in the mix to make this work, and that is we have a code generator. And the code generator lets us take a UML domain model, which is a class diagram, and it turns it into, at the moment, MongoDB with a collection per class and Node.js. And each of those classes has all the common database access functions, what they call the CRUD functions, create, read, update, delete, all code generated. And it turns out that doing that code generation at inception on the project enables large teams to communicate together more effectively and to integrate their work. Okay, so we run this code generator right up front at the beginning, and then we go through use case, decompose our use cases into model view controller, and then we do testing, and we focus on acceptance testing while we're optimizing and tuning the software. So that's the spiral model on a per use case basis. So basically, again, I'm going to be a little bit from the Department of Redundancy department today. And if you haven't heard of the Department of Redundancy department, you will when you graduate. But basically, we split the system into its use cases, and then we run through this spiral model life cycle on each individual use case. And everybody's working in parallel. So what happens when you do things in parallel is that the number of hours you work doesn't really change that much, but the time on the calendar changes dramatically because everybody's doing that work in parallel with everybody else. So you can get quicker schedules and shorten your time to market. And shortening your time to market is a big deal, okay? And so you can do large systems by just adding more people to your project. So when we set up for parallel development, what we're going to do, again, is we're going to generate a REST API from a domain model. And that REST API, which in our case is Node.js, the REST API includes all the common database access functions, right? So if you go back to my mobile coupon system, if I had a coupon as an object in my problem domain, then I draw a box on my UML class diagram, and I label it coupon, and I put whatever attributes it needs in it, you know, like the dollar value or whatever, the expiration date, whatever attributes a coupon needs, image. And then you run the code generator, and then I have the ability to create coupons in the database, read coupons from the database, update coupons, delete coupons, right? And it just happens, bang, right at the front of your project. I put this infrastructure in place. It's basically the database infrastructure for my project. It gets put in place immediately, and then I can start working in parallel. Okay? So I model the problem domain. I generate my database access code and my API from that domain model. And then I partition my system into use cases. I organize them into packages, and I start assigning developers to the use cases. So when you're assigning developers to the use cases, now you care about what's the background of the developer. So if my system needs an iPhone app and an Android app and a web app, okay, I'm looking for iPhone developers, Android developers, AngularJS developers, right? And we've been doing this in CS590 on multiple projects for the last few years, and we've assembled some pretty interesting data from it. So we've taken the code generator, which started out as PhD research from a student some of you may know named Bo Wang. So Bo was working on this code generator as part of his PhD research. Bo was in that initial CS577 class that did the mobile coupon system. And we developed this design pattern and got him his thesis topic after that class. So we've now taken that code generator and commercialized it into something called the Parallel Agile CodeBot, which you can try for free on parallelagile.com. You get everything except the server-side database code. And it basically, in under a minute, it creates all this stuff. So I start with a class diagram, which is my domain model. And 60 seconds later, I have a Mongo collection for every box on my class diagram. I have Node.js code to create, read, update, delete stuff in Mongo. And then I have API documentation, and I have a JavaScript client and a Java client. Okay, so I have client-side code, server-side code, and it basically is all this database infrastructure for the project. Comes for free before you really get started doing any developing. Okay, and then this is from one of our test projects, which is called KarmaCam, which is turning into a viable business in its own right. So KarmaCam, this is the KarmaCam architecture. We have an iOS dashboard camera app, we have an Android dashboard camera app, we have an AngularJS web app. We also have a bunch of machine learning stuff that got added after this diagram got drawn. All of these things communicate through Node.js and talk to Mongo in the cloud. Oops. So since then, we've added TensorFlow and Python clients that also use the REST API. One of our other projects is a game project called TQMan Go that uses Unity 3D instead of AngularJS. Unity kind of replaces, the app. We build an iPhone app and an Android app from Unity, but it still communicates to Mongo through Node. Okay, so KarmaCam is a mean stack app, and we've had over 100 CS590 students work on this system over about the past 3 or 4 years. And it's pretty interesting, actually. But it started the very first class of the very first semester that we worked on KarmaCam. This was the idea that you can. So I started KarmaCam because I got upset at a bad driver who made an illegal U-turn in front of me while I was driving to my consulting job, and I realized that I could go get CS590 students to go build this thing for me, right? So first day of class, so we now call them traffic incident reports and not bad driver reports because people had a bad reaction to the term bad driver report. But the initial domain model was I have a bad driver report. It has a video attached to it. It gets posted to my account. So the report poster has an account. We have independent reviews on this. So it's a crowdsourced app, and we basically took this domain model, generated an API from it, and then started prototyping right away. Okay. So now the CodeBot generates API documentation. So here's the one of the things we were building was machine learning video cropping tool that cropped the video. Instead of the 20-second default video that we get when we upload the thing, for training the machine learning stuff, you want to focus that in on only the 1.5 seconds that shows the incident. So this is we have an incident start and an incident end, and we have an image for each of those that goes through computer vision, OpenCV, TensorFlow analysis. But we generate that, and so you can get, put, post. All these functions are just built for you, and you don't have to code them by hand. And if you've ever had to build these by hand, it's a lot of work. It's a lot of work, and it's kind of boring, repetitive code, and it's error-prone because it's boring and repetitive. So having it generated is a pretty great benefit. So you basically don't need to write this whole database access layer of your applications by hand at all. Okay, that's all just built for you. And if you try the CodeBot on the Parallel Agile website, what you'll find is that your API is actually automatically hosted for you on AWS Lambda. So you run the code, you basically draw a class diagram, generate the code, and your API is live and ready for testing on AWS Lambda. Just immediately. So we put a lot of work into this infrastructure. Once your database and API is generated, then you start going through use case analysis. And the use case analysis is first you split your system into its scenarios. And then you can do either of these or both. But if your use case is high risk, and what I mean by risk is kind of technical risk. Like, for example, in KarmaCam, when I first started speccing this system out, I was pretty intent that it was going to have a voice-activated interface. So I would actually talk to my phone on the dashboard and say, now go upload this video. And so we prototyped it. We prototyped it with 2 different voice recognition toolkits, and we acceptance tested it. And we got it so it worked in the classroom, but when you put it in the car with ambient noise, it wasn't reliable. Sometimes it wouldn't upload videos. Sometimes it would upload videos when you didn't want it to, and we just couldn't get the reliability to where we wanted it. So we backed off to a one-touch interface. Just tap the screen and it uploads the video. It works much better. So anything that's high technical risk, we absolutely prototype it. If it's straightforward, like, account management login, sometimes you just write the use case, discover what the requirements are. And then my background on this is I've written half a dozen books on use case driven development, which you can find on Amazon if you type my name into it. But one of the keys to doing use case driven development successfully is you take your use case description and you turn it into models, views, and controllers. Okay, you guys all know the MVC design pattern. Most people think of model view controller more as a code level design pattern, but it turns out the right way to do use cases is you apply an MVC pattern to the whole use case description. So use case has a sunny day scenario and a bunch of rainy day scenarios, corner cases, edge cases. And what you want to do then is think of that use case in terms of what's the database access look like? That's the model. What's the screens? What do the screens look like? That's the view. And then what's the logic that glues together the view to the model? Those are your controllers. Okay. And when you decompose a use case into MVC, you find all kinds of mistakes with it. And so I've written a bunch of books on how to do that, so I kind of already had that knowledge going in, and that's all baked into Parallel Agile. But the key is it's one use case per developer, so all of this modeling isn't going on at this big 3-month chunk of time at the front of your project, what they call big design up front, which the Agile people hate. It's all going on in parallel, and so the schedule time is compressed. Okay. And the key thing about Parallel Agile is its schedule compression. I mean, that's really the big overriding benefit of it. So then we would take that use case and we would storyboard it out. So this is a storyboard that we did. This was one of my students named Asmita. Did this in CS590 the first semester. You can see it then. It was called baddriverreports.com. We didn't have KarmaCam. We didn't have it named KarmaCam back then. But first she storyboarded it. I approved the storyboard. Then she prototyped it in Angular. And that works. You kind of get a bare bones up and running, piece of code. And then we fleshed it out since then and made it look better and added some refinements to it, right? Again, this all happens one use case at a time. People are storyboarding their use cases, prototyping their use cases, designing their use cases. So this is the model view controller diagram. That's the view. That's the screen that the user's looking at. This is the database, videos, bad driver reports, captured images. The logic in between is these controllers. Okay, so it's model, view, control. And that translates at the design level into sequence diagrams that look like that. Okay. And the key focus here is, do I have all my corner cases and edge cases identified when I do that? Because most of the bugs in software systems happen from edge cases and corner cases. Sunny day scenarios are the easy part. So one of the things we built as part of our toolkit, and we developed this tool is Spark Systems Enterprise Architect. They're probably the leading market share tool for UML modelers. So we developed an add-in that hooks up to our code bot. The add-in is free, and one of the things that we built in it is a use case complexity analyzer. Because if you have this level of description, you can actually analyze these diagrams and see, if this diagram is 4 pages tall, okay, that's a really complex use case. We probably need to split it up. So we just count how many things are inside the use case, and we say, that one's pretty straightforward. Some of these are pretty big, okay, and you might want to consider splitting them. And the reason you do that is that we're trying to set up a project lifecycle where each trip around that spiral takes about a month, okay? So you have a month for proof of concept, a month for MVP, a month to optimize it, and then you can release it in 3 months. And the scope of what you can deliver in those 3 months depends on how many programmers you have working in parallel. So if you have a big system, you get 50 or 100 developers working in parallel, you can knock that whole sucker out in 3 months, okay? But in order to do that, you need to know that none of your use cases are going to take more than a month to do. So we use this complexity analyzer to split those things, help split those things up. And then in testing, we focus on acceptance testing, and we focus on edge case and corner testing. So we actually generate acceptance tests. This is from, really we took it from a book that I wrote about 10 years ago called Design-Driven Testing, where we built some scripts into that same enterprise architect tool, this tool. There's another add-in for this that has logic for design-driven testing, and it generates test cases from requirements, from use cases, and it actually generates some JUnit kind of stuff as well. The big reason that we focus on acceptance testing instead of unit testing, because most of what you read about, especially on Agile, is JUnit kind of unit tests, right? And it's all unit test, regression test. The problem with that is that you only write unit tests for stuff that you're thinking about. And the big problems in software projects come from the stuff that you forget about. I forgot that corner case. I forgot that edge case. So Parallel Agile as a process has built into it a focus when you're doing your modeling on identifying all those edge cases and corner cases and then making sure all of them get tested. Okay. And, if you forgot about the requirement to begin with, you're not going to have a unit test for it. So you're going to get this green bar, JUnit green bar that lights everything up green. It doesn't mean anything because it's only showing you the stuff that you remembered to think about. It doesn't help you at all in the hard part of software testing, which is testing all the edge cases, corner cases, rainy day scenarios, exceptions, right? So that design-driven testing stuff works from this thing that's called a structured specification for your use case. So here you can see these are all the steps of my use case. And then these are, A is for alternate, E is for exception. So those are alternate cases and exception cases. So I'm looking for a report here. There's an exception. There is no report. Or I want to change my sort criteria to change how that report displays. That's an alternate behavior. We generate this logic tree from that description. Then we generate a test case for each path here. So sunny day scenario all the way through, exception case, and alternate case. Okay, and those get generated into human readable English acceptance test scripts. And so what we're trying to do is go faster without increasing your defect count, okay? You can generally go faster on a software project by cutting corners and not worrying about your rainy day scenarios and sweeping them all under the rug. And some Agile methods, extreme programming, for example, has an acronym for do the simplest thing that can possibly work, okay? Well, the simplest thing that can possibly work is you just code the sunny day scenario. You don't worry about the rainy day scenarios. You can get that up and running fast, okay? But if you try and ship it, it's full of bugs, right? So we're trying to go faster, but without increasing the defect count. So you need to test those corner cases and edge cases. On the project management side, we use something called, I call it a sprint plan. And so the blue boxes here are user stories. So I'm not sure if you can read this, but as a user story, I want better video quality, okay? And so a task, the green are tasks. So blue is user story, orange is epics, and the green are tasks. So this is how I organize the projects. And so the task underneath better video quality is implement camera settings, okay? So I have low light mode, for example, on my camera, right? So, and then I assign the tasks. Each one of these tasks goes to a CS590 student, basically, right? So CS590 is directed research. They sign up. I organize, I recruit my team, see who I got, and then I assign them tasks this way. And I track my project management. So it's very much the Agile project management paradigm, but with some UML technical design added in. So one of the pieces of conventional wisdom, and it's called Brooks' Law. Have they taught you Brooks' Law yet in here? Brooks' Law says you can't make a late software project go faster by adding developers. Okay. And Brooks' Law has been around for about 50 years now. Okay. Fred Brooks, when he wrote Brooks' Law, he worked for IBM. He was a manager of a big, huge project called OS 360, which was a massive operating system for a big IBM mainframe in like mid-1960s, early 1970s. Okay. The premise of parallel Agile is, sometimes you can actually accelerate late projects by adding developers. And we do this all the time in the CS590 projects. When you have a group of people working on tasks in parallel, there's basically going to be three outcomes, okay? They're either going to complete on time, they're going to complete early, or they're going to run late. It's only three possible outcomes, right? If you take the people that complete early and you put them back into a resource pool, you can add them to help the people that are running late. I do this all the time, and it works well. The good news about this is that usually the people that complete early are your most capable developers, okay? So you get your smartest and best developers complete their tasks early, and then you can add them, and as a generalization, the people that run late are not your strongest developers, right? So you can take your strong developers and give them to, have them help the people that are running late. Actually, it works well. I do it all the time. I do this in CS590 routinely. So I've never been a fan of Brooks' Law, and I'm trying to repeal it, actually. So one of the things that happens when you're working with large teams of developers is that you have to keep track of multiple source code baselines. So we have, for example, on KarmaCam, an Android baseline, an iPhone baseline, a web app baseline. Now we have a machine learning baseline as well. And every week during the semester, we're integrating work from different developers into our baselines, and then build the baseline and acceptance test it. Okay. So our project GitHub for KarmaCam has like a crazy number of baselines in it right now. but these are real things that we were working on last semester on KarmaCam. So baseline management becomes pretty important. So now there's the question, what if you don't have a large team? And most of the industry has been told for so long that they can only do small team agile projects that this is pretty much the situation that we're going to encounter most of the time. So what you can do is you can basically kind of devolve this back down to Scrum. But you can still take advantage of the code generator. You can still take advantage of the acceptance test case generation. You just have to, the project management is a little different. So, so my co-author, Chuck Suschek, drew this diagram. There's different things that you can vary and you can fix. So, in Parallel Agile, we fix the scope and we fix the time, but we vary the team size, okay? Whereas in Scrum, your team size is fixed, and the sprints are fixed at 2 weeks, but the scope changes, okay? So your scope is, what can my small team accomplish in 2 weeks? But when you do this small team agile stuff, you have to do all this backlog management. And you have product backlogs, you have sprint backlogs, and your user stories go in the product backlog, and you take them out, and you put them in the sprint backlog, break them into tasks, and then the small team goes through and they chunk off these tasks over 2 weeks. And there's a lot of moving parts and pieces. A lot of companies get it wrong. When they get it wrong, the projects kind of break down. It's much simpler to just get a large team and have everybody work in parallel, if you could do it. Okay, you can't always do it. But this backlog management is its own beast, I guess. And Chuck wrote the Scrum chapter in the Parallel Agile book. So some people may want the book just to learn how to do Scrum correctly. Chuck is involved with the Scrum.org people. He's like the responsible for their project owner role, I think. But you basically have this, I take my product backlog, I take some tasks, I move them into the sprint backlog. They go from the in process and complete. And you're all working in this tiny 2-week space. So you have to go through this big, Kanban board, Scrum board thing every 2 weeks. It's not for me, but that's what mostly goes on in the industry. And the problem is, you're just in this never-ending cycle of 2-week sprints. And you don't get done very fast, which is not very satisfying for me. So part of what we're doing on KarmaCam is machine learning. So we're doing OpenCV, TensorFlow, image analysis. So we have vehicle detector, stop sign detector, red light detector, license plate reader, and we're following the same life cycle on that of proof of concept, then MVP, then optimizing. So we've done the proof of concept. We're doing AI scoring of incident reports. And just as an example, suppose I report a car for running a red light, and I upload a video that shows that car running a red light. What we're going to do is we're going to score that report by saying, we're going to run the traffic light detector and says, is there a red light in the video? Okay. If there's no red light in the video and it was reported as running a red light, then we're going to score it kind of low. Okay. We have a license plate reader. Can we read the license plate number that was reported in the video? So if we can't find, if OpenALPR can't find the car by license plate anywhere in the video, we're going to give it a low score. But if we can find the vehicle that got reported and a red light in the image, then that score is going to go up. And we're using machine learning that way to pre-screen what our human reviewers are going to look at. We're not eliminating human reviewers because I don't trust the machine learning stuff yet. But we're going to pre-screen all the incident reports using ML that way. So this is our actual sprint plan diagram from 2 or 3 semesters ago. And those are the names of the students that actually were working on that. Some of these students actually wound up on my payroll. So this is basically scoring the videos for dangerous driving. And then we're actually doing DUI detection. So we're actually just looking at raw, unannotated video, and we're looking for vehicles that are weaving around doing multiple lane changes at high speed using ML. And we're routing those videos that pass that screening directly into an app that we've designed for law enforcement to be able to get the drunk drivers off the road quickly. The reason we focused on this problem, just by the way, as an aside, is that it's a huge problem. I started doing it. I started the project just because I got pissed off one day at a car that almost caused me to have an accident. And I started researching it once we started building it, and the numbers are staggering. In the U.S., someone gets killed every 15 minutes, somebody gets injured every 15 seconds, and there's $1 trillion a year worth of property damage. So it's one of these big societal problems that no one's figured out how to do anything with it. So I'm happy it's made as much progress as it has. So this is part of what we're doing in CS590. This is the DUI detection stuff. What you need to detect drunk drivers is you need to be able to detect vehicles. You need to be able to track them across multiple frames of a video. You need to be able to identify lane boundaries. You can see this one was not quite perfect. Okay, still tuning that one. And then you look for a vehicle like this one that's crossing the lane boundary. You can count those things. And you need a different kind of TensorFlow beastie called an LSTM, which stands for long short-term memory, to put those things together. So that's some of the stuff we're working on for KarmaCam. I'm going to guess you've had a lecture on ICSM. Safe guess in this class. So basically, if you've seen, so this view of ICSM is basically this spiral unwrapped into a linear view, right? This spiral simplifies into this, okay? And so it's proof of concept. Here it says concept of operation, minimum viable product out in here, and then optimized. And of course, you can go multiple times around this optimized loop. So each one of these phases would take about a month. We've spent 2 or 3 passes on optimizing, KarmaCam now, because that's how we're doing it. This is also out of the ICSM book. This is Dr. Bain's chart. The key point on here is that we don't only do the development in parallel, we also do testing in parallel. So as soon as somebody completes a task, we try to run it through acceptance testing immediately. And ideally, when you staff these projects, you have a team of testers that's working alongside of the developers. Typically, I try to get about 1 tester for every 3 developers. That seems to be a balance that works. So the unique thing about Parallel Agile, as far as I know, is that it gives you a chance to deliver a pretty large project in 3 months. There's no other software process that I'm aware of that gives you that same opportunity to do that. So we think we're onto something. That's kind of the first pass through the slide deck. So let me go to the second one, while I'm doing that, if anybody has questions, I can take them now. And Cam, we're going until 3:20, is that right? Okay. Anybody got questions? Nope. Okay, so again, these are going to be kind of redundant. They're basically the same pictures, but the emphasis is going to be a little different. So what we want to do is let large teams get projects done faster than small teams can. And really what we're trying to do is we're trying to leverage parallelism as an accelerator of things. So parallelism is always what you do to make things go faster. But typically it's not really exploited in software engineering. So easy example in hardware, multi-core processors. Okay, my Pentium 5 runs faster than a Pentium 3. Why? More CPUs. Okay, so if you think about a developer, and I apologize if it's impersonal, but you could think of each of you sitting here in the class kind of like a CPU, right? Your job is to get some development task done, right? So if I have more developers, I should be able to go faster. In electronics, and my degree's in electrical engineering, you learn this in high school physics, right? Resistance in series versus resistance in parallel. And when we got I thought I had another slide, but when we got that first result of 27 hours per developer, I looked at it and I said, we just got that. Okay, we just did resistance in series versus resistance in parallel. These are like 2-week sprints. Sprint 1 is 2 weeks, sprint 2 is 2 weeks, sprint 3, sprint 4, sprint 5, and it just adds up linear on the calendar. But when you're able to have people work in parallel, it collapses your schedule. So Agile methods typically don't support parallelism. They're very much stuck on a small team metaphor. And a lot of Agile projects have attitudes about it. So if you're the customer, you come in and I say, well, I want to get this 4th thing done. Sometimes your Agile team will say, well, you didn't tell me what you wanted us to throw away from the other stuff, so we're just going to throw all your stuff away and build which one. I didn't draw this cartoon. This stuff actually happens in the industry. It looks like it wouldn't. So it's spiral model, but it's spiral model in parallel per use case. Every developer working in parallel with everybody else. And this is another one of Dr. Bain's curves. I think what you guys are probably still using in here is architected Agile. And what we think is that, we're pretty close to the cost minimum here. This is an interesting curve just to think about in terms of software development processes. The Agile processes are feedback driven, and the more waterfall design oriented are plan driven. Okay, and what this curve says is that under planning is expensive and over planning is expensive. Okay, somewhere in between under planned and over planned, there's just enough planning, and that's what we're shooting at. And the reason these become planning is that the planning cost is expensive, but the refactoring cost is also expensive. If you don't plan your project enough, you spend all your time rewriting it and rewriting it and rewriting it. And that's there's never enough time to do it right, but there's always enough time to do it over and over and over. And you'd be amazed when you graduate and get into industry, that's actually how most stuff works, right? So, yeah, that's the slide I was thinking of. I did have it. So, when you boil this down, 26 hours, that's 4 8-hour days, right? 4 times 8 is 32, so 26 is less than 4, just call it 4 days, because everybody's got to eat lunch, And when I saw that number, 26 hours, per student, I said, yep, that's, now on the schedule, I can collapse everything down. But I'm not crazy enough to say each of our sprints should only be 4 days long, okay? Not going to go there. So I set it at a month, okay? So what, if you really wanted to, push it, and this is for prototype, not for full-blown designed and tested code, okay? But it's still, you could collapse the schedule pretty dramatically. So the projects we've been doing this on, we started with the location-based advertising. That was 47 students. We actually took that all the way through to commercial deployment over a few semesters. We did a small experiment, picture sharing. We actually did that one in here also. We took two groups, two 577 project teams, and had one do architected Agile and had one do parallel Agile. Experiment was kind of got not a perfect experiment, but we did pretty good on the picture sharing one. KarmaCam has been the biggest proof point. That's had over 100 developers on it, and we've been around that optimized spiral a few times now, adding a lot more capability. We didn't start out doing any machine learning stuff, for example. And then a game project, Tiki Mango, is looking pretty good. If anybody wants to test our game, you should email me. It's a Hawaiian-themed AR/VR Pokemon Go knockoff. So you blow up animated 3D Tiki Ben with lava fireballs. And it's built in Unity 3D. We're having a lot of fun with it. It's going really good this semester. So we actually have test builds that are downloadable now. And if you want to test the game, shoot me an email. So basically, what this comes down to, and again, these slides are focusing on the cost and schedule impacts of parallel, right? So what it comes down to is you can run each of these phases at about a month, and you can get something that's been through prototyping, proof of concept, design, including corner cases, edge cases, optimized, tuned, and acceptance tested in about 3 months. And the size of that system depends on how many developers you can get. So where we think this is going to probably have its first big impact is going to be some of the offshoring companies, where over in Bangalore they have a staff of 200 programmers, right? We think that those companies will probably be some of the early adopters of parallel, and what will happen is if you hire one of those companies that says, yeah, I can put 50 of my developers on this project and get it done for you in 3 months, and they deliver a few of those companies are going to start winning in the market, right? Because time to market is most everything. And, the way we kind of did the math on this is we've been running CS590 projects. In CS590, you get 5 hours of work for each unit of directed research they sign up for. So if they sign up for 1 unit of DR, I get 5 hours a week. If they sign up for 2 units, I get 10 hours a week. They recently added unpaid interns. They work 20 hours a week. It averages out somewhere like 10 to 15 hours per week per student. And the semester may be calendar 16 weeks, but you don't get 16 usable weeks because there's midterms, there's finals, there's job interviews. And so we just normalized it to say, 1 semester of a directed research student is about a calendar month, right? It's not exact month, 30 days, it's a rough unit of measure. In fact, these student projects, I believe, are way harder because one of the things, and it's been the hardest thing to do across all of these projects, is I get a new group of developers every 3 months. I basically got to start clean. And so somehow you have to maintain enough context and history to allow that to work. And the things that help that are, number one, having a UML model, and number two, having the API and the API documented. Because I could say, here's all the use cases, here's the database documentation, how to access our API. Now pick up this use case and run with it, right? And, but don't try this one at home, okay? 100% staff turnover over 3 months, really hard. All these gray hairs, didn't have all those before I was doing it. So again, generating the REST API from the domain model allows integration of the work of a large team of developers. So we generate that database infrastructure, and this is kind of 3 or 4 of the earlier slides all collapsed into one. We start with a domain model, and we generate all these pieces. Mongo, Node, Swagger API documentations, client-side code, all of that just gets built. And it adds up as roughly 500 lines of bug-free database access code for every class on that diagram. Okay, so if I go in with 20 classes, 20 collections in my database, times 500 lines of code, you can see I'm getting a little boost, okay? So we're going to get to how big of a boost are you getting in a few slides here, because that's what we're trying to quantify it. But we've tested this on our test project. We've got mobile apps, we got web apps, we got machine learning stuff, and it all goes through REST API hooked up to the NoSQL database. So the reason this works, this is kind of the why it works in terms of Brooks' Law. When Fred Brooks wrote Mythical Man Month and said you can't make a project go faster by adding programmers to it, the reasons were basically, the 2 biggest reasons were communication and integration, okay? So when you have a large team of developers, they all have to communicate about what the design is, right? They all have to have a common understanding of the design. Well, in 1960, whatever, when Fred Brooks wrote that, there was no UML model. There were no use case diagrams, sequence diagrams, class diagrams, none of that stuff, okay? And there were no REST APIs and API documentation. That stuff didn't exist. So it's the REST APIs that get you the integration, and APIs are typically how what they call B2B, business to business integration gets accomplished, is by REST APIs. So if I want to make my Tiki Man game log in with Facebook, which is actually one of the things we're doing right now, okay, what we do is we go get the Facebook APIs, and we write a login that uses the Facebook APIs, and that's how my project, which doesn't know anything about Facebook login internals, can integrate with Facebook, right? So we're applying APIs on a per developer basis. All the developers are using the same API, but it's not that each developer publishes their own API. It's that all the developers use the API of the problem domain. So the problem domain itself has an API. And if everybody understands the problem domain, they can understand it at a conceptual level. From that diagram, they can understand it at a, now I want to create one of these bad driver reports in the database level from the API documentation. So this code generator helps with communication, helps with integration, and that's why we're taking a crack at Brooks' Law here. So kind of skip to here. I got 20 minutes left. If you think of the inside of the use case in terms of model, view, and controller, okay? It's not an exact number, but roughly you can say a third of my work is going to be in the user interface, a third of my work is going to be in the database infrastructure, and a third of my work is going to be in the logic, okay? Not exact numbers, it's going to vary from project to project, but really that database layer, that database infrastructure, especially when you get into all the exception handling with database errors, sorry, my network connection went down, I couldn't write to the database. All those exception handling is handled in the code generator. You're going to cut your cost by around a third if you can generate the whole database layer, okay? Round number, around a third. That's not where most of your schedule compression comes from, although that will also chop a third off your schedule. The big win in the schedule compression is from the parallelism by having large teams develop in parallel. Okay. So, and then the testing, focusing on the edge and corner case testing, is basically going to reduce your defect rate, and defects are expensive, and it's going to reduce your refactoring rate, and refactoring is expensive. So a little bit more planning gives you a lot less refactoring, and focusing your testing on acceptance testing as opposed to unit testing is going to basically attack the places where software breaks, which is your corner cases, edge cases, missing requirements. And so you're going to save money there. So you get cost savings. Typically, in industry, what you'd find is that there's a software test team, a QA team, or in aerospace they call it IV&V, verification and validation, independent verification validation. This is what those people normally do. So now we're giving them tools to make the communication between the developers and the testers more efficient as well. So having the testers work in parallel with the developers, it's another thing that saves you schedule, because I'm a developer working on my small task. I push it. It immediately goes to a tester who checks it out, says, yeah, that's right, but you forgot this, right? That feedback loop happens very fast. That feedback loop, the faster it happens, the more time you save on schedule. Okay. So the big win on parallelism is being able to put a different developer on each one of these green boxes here, okay? Because one user story here translates into a bunch of different development tasks. And I can split all those out in parallel and get them done at the same time. And what happens is you have to think about dependencies, okay? Because these tasks are interdependent. That's one of the complex things about software. The interdependencies affect your baseline management, and they affect the integration order. They don't affect when the code gets written. Whereas on a Scrum project, they basically say, well, we're not going to be able to complete this much in 2 weeks, so we'll write that part later. This lets us write all the green boxes get built in parallel, but they get integrated in a specific order based on dependencies. Okay. So we use this tool to make sure that no task that gets handed out to a developer, none of these green boxes should take more than a month to do. And if you can estimate so that none of those green boxes take more than a month to do, and then you have all the green boxes built in parallel, they're all going to get done in a month. Okay. So that's why we use this use case complexity analyzer. And your cost per phase is basically the number of developers you have times the average pay rate of your developers, right? Really simple. And I'm going to guess that you guys would get exposed to Kokomo kind of cost estimation in here as well. So there's Kokomo cost drivers. These are programmer capability, language experience, environment experience. Where those become important is not so much in estimating your cost, they become important when you're staffing your project. So what's important to me is that if I'm doing machine learning screening of potential DUI video, I need people that know how to use OpenCV, TensorFlow, and Python, okay? So that's where and I need really good ones, right? So the capability and experience drivers come in when you're filling in so it's allocating the developers to tasks. That's when you consider those things. They're still important, they're vitally important, but they don't necessarily impact the schedule and the cost. Well, they impact the cost if you do it wrong, if you put the wrong developer on the wrong task. Okay. So sometimes you can accelerate a late project by adding developers. And the good news, if you try to do this, is that it's almost always your best developers who finish early. And so those, so I use kind of a SWAT team metaphor on my projects where I have this core group of people, especially if I'm lucky enough to get a student that repeats from one semester to the next. They go on my SWAT team, and whoever's stuck, I send my SWAT team to help them. Okay. So the dependency management affects the integration order into each of these baselines. Okay. That's where dependencies come into play. So if you don't have a big team, you still save some money using the code generator. You still save some money using the acceptance test generation, but you can't deliver a big project in 3 months with a small team. Just can't do it. This backlog management stuff, by the way, is really expensive. So most of your cost, or a lot of your cost on Agile projects, is spent on daily scrums, backlog grooming, retrospectives, all this stuff. That stuff all costs you time and money. With Parallel Agile, your time is basically spent coding, debugging, and testing, and a lot less time on backlog grooming. So KarmaCam is our biggest proof point so far. If you want to check out the website, it is karma-cam.com because someone already owned karmacam.com and we haven't paid them the ransom that they want for it yet. But it's a really nice website, karma-cam.com. It's got crowdsourced traffic incident reporting, including AI scoring of incident reports, real-time alerting, parking enforcement, and these technologies, MeanStack, Android, Java, iOS, Swift, AngularJS, Python, TensorFlow, have all been used on this project. Been over 100 CS590 students with a turnover rate of about 90% across semesters. Turnover rate is hard. So, I'll leave a couple minutes for questions. Basically, I want to try and put some numbers on this faster delivery, fewer defects, lower cost. It's faster because everybody's working in parallel. It's faster because you're code generating the database and the API. It's less buggy because you're actually spending the time to design your use cases carefully and figure out the corner and edge cases. And then once you figured out the corner and edge cases, you make sure that none of them get forgotten when you do your acceptance testing. And it's cheaper because we're using automation, code generation, and test case generation. And it's cheaper because a little bit more planning buys you a lot less refactoring, and refactoring is expensive. So now the bottom line number of the whole slide deck, what's possible, okay? And this is me speculating, okay? So I want to be clear that this is speculative numbers, but they're based on the test projects we've been doing. I think you're going to save about 30% cost. And depending on how big a team you run, I think it's going to average about 80% faster to deliver. And you're going to have about half the number of bugs. Okay. So for us, if these numbers are real, 30% cost savings, 80% schedule compression, and 50% fewer defects, we're on to something pretty big. Okay. And that's what we've been doing. If you'd like a copy of the book, email me. And have 10 minutes left for questions. Well, no one's sleeping, but no one's asking questions. So, in which case, we'll finish 10 minutes early. Thank you for your attention. And
This concludes CS577A. Today is Monday, October 14th, 2019.